So section 4.7 is going to ask us to work on optimization problems. So these are nice applied problems where you're trying to use calculus to try and either maximize or minimize something of interest. The first problem we're going to work on is trying to maximize the volume of a box. And that box is going to be made from a sheet of paper. So each of your groups was given a sheet of paper that started out like this. It started out as just a bunch of little squares, and the distance is 14 one way, 18 the other way. And I cut off little corners and then folded it in. So I cut off a corner like this, size of X, and then folded it into a box. And you calculated the volume of the box. So let's take a look at those calculations first. Depending on how many how many corners were cut out, so 1, 2, 3, etc. Now, if you don't cut out any corners, if you don't make any cut at all, you can't fold this up into a box, the volume would be 0. To tell how many of these squares were cut out of the corners, just look at the height and count the number of squares that represent your height, the height of your box from the bottom up. So 1, 2, 3, 4, etc. So who had the box with one square taken out? Where was one? All right. What was the volume then? 176. You sure? Okay. So how about 2? Who had 2? What'd you get? Good. 280. All right. Who had 3? No, the height of 3. So what was the volume of your box? Good. 288. 4. Who had 4? All right. Good. 240. 5. Someone have 5? Let me help out here. 5 was 160. Actually, 166 maybe. Won't matter. How about 6? 64?
Yes,
Okay. That seems reasonable. 64. Now, let's think about what happens if you would try and cut out 7 squares. If this is 14 wide, and if I cut in 7 this way and I cut in 7 this way, so let me zoom out a little bit more. There we go. So if I cut in 7 this way and 7 this way, what's left? Nothing, right? So you've gotten rid of one dimension. So 7 is too much. You can't cut out 7. You'd be kind of at the same place you're at 0. How about 1? What do we get for 1? 192? That sounds better. All right. So obviously, the cuts that you make makes a difference, right, in terms of the volume. If you wanted to design this to be the best that you could be, to get the most volume, then what should you do? Well, your cut's certainly someplace between 2 and 4. Now, I don't know if the maximum occurs between these two or between these two. Does this go up and then down, or does it keep going down? Don't know. So let's apply some calculus to this problem. This is a nice example of what you're going to do in general. You're going to start out with a little picture. And that picture is going to help you out. Now, not every problem is going to be something for which you can draw a picture. Our first couple to really get going on this are going to be problems without pictures. But this one's a good one. When I fold this up and get this rectangle over here, what's the length of this side going to be? It started out as 18. When I fold it up, what's it going to be? Almost. 18 minus 2x. So that would be that side. How about this side right here? This started out as 14 one way, so what would this side be? 14 minus 2x, and the height, of course, is x. So that's your height, and depending on the height, the volume of your box is going to change. Let's see if we can't figure out the volume of that box. What's the formula for the volume of a box? Length times width times height. So this times this times this. So x times 18 minus 2x times 14 minus 2x again. Do you want me to do this out in slow-mo, or do you want the happy ending? Which one? Happy ending? Okay. Foil those two together first, and then distribute the x. You get 4x cubed minus 64x squared plus 252x. So the first thing you do is you draw a good picture, if that'll help you. Yeah, if that'll help you. Then you create a function of one variable. And it's important that you have a function that depends on one variable. This is Calc 1. We don't know how to deal with more than one variable. So function of one variable. Underline that for yourself. Now we need to consider the domain, not necessarily of the function, but the domain as it applies to the problem. This is a polynomial. Polynomials have a domain of negative infinity to infinity. But I can't exactly consider negative infinity to infinity for this problem. I mean, at some point you're taking out too much material and you don't have a box left. So what's that point? What's the most that I could take out of either of these? I guess I want to look at this side. That one's going to be the more restrictive. What's the most that I could take out? 7, right? We kind of saw that. Yeah, 7 with a parenthesis. You're exactly right, because we don't even want to go up to 7. So our interval of interest is going to be 0 to 7. And I get parentheses, nice observation there, because, well, if I don't take out at least a little bit, then I've got no height. And so I can't form a rectangle. If I take out too much, then again, I've got no width, and I can't form a rectangle. So it's between 0 and 7. Picture, function, interval. And the last thing to do is do the analysis. When I grade your exams, what I'll do is I'll set up a little series of partial credits. Like, okay, if you get this step, that's a couple points. If you get another step, if you get the interval, it's another couple points. If you do the derivative correctly, another couple points, etc. All the way down. So it's a series of little pieces of partial credit. The last part here is the analysis. We want to figure out what value of x maximizes the volume of the box. So, okay. Here's our function. V of x equals 4x cubed minus 64x squared plus 252x. How are we going to figure that out? Well, we don't want to set it equal to 0 just yet. Where? You could factor out an x, but remember our objective is to maximize the function. So how are we going to find the value of x that maximizes that function? Find the derivative. We need to find the critical points from the derivative. Critical points are where the derivative equals 0 or does not exist. Are there going to be any places where the derivative doesn't exist here? No. So we're okay there. Let's find the derivative. V prime of x. Andrea, what would V prime equal, please?
12x squared minus 128x plus 252.
Great. Matt, want to set that equal to 0 and solve for us? I'm kidding. This is not one that you can factor in your head. In fact, you can't factor this one at all. It just doesn't work. But we do need to set it equal to 0. Now, if you're stuck setting this equal to 0 and solving, what are your choices? You don't have real good choices. There's really other quadratic formula. Exactly. Now for myself, I think I might factor out a 4 here and then work things. So if you do a 4 times 3x squared minus, this would be what, 32? Yeah, 32x plus 63 equals 0. That might make it a little bit easier, but even then, it's kind of a pain. So, before I give you the quote-unquote happy ending, let me share with you a little calculator trick that you may have depending on how well up to date your operating system is. So this is on the TI-84. So go to the apps button. Go to the apps button and look for Polynomial. This is a key that can get a lot done for us. So go down, so hit the apps button. It's third row, second column. Polynomial 2. And let's press the first option. We want the polynomial root finder. So select the first option. It's going to ask you what order of polynomial you'd like to use. We're dealing with a quadratic equation, so it'd be of order 2. Then, let's see. You can set this to auto or decimal. I like having it a decimal because it's just going to give me a decimal value. Auto will show you fractions if fractions are applicable. Once you get it all set up, then press enter. And then enter in the coefficients. So the first one is 3. Skip past this. Just leave it as a plus, and then enter in a minus 32 for the next one. Press the arrow to the right for a little bit. Get to the third one. Enter in 63. Once you have 63 entered, press solve. And this is really cool. It's going to give you nice decimal values for both solutions. Yay, cool. You like that one? No? You don't like this? You'd rather do it by hand? So I'll tell you what. You race me. Come up with the numerical solution by hand. Yeah. All right, so if you're old school, that's fine. Old school, when you do this, you're going to get 16 plus the square root of 67 over 3, and 16 minus the square root of 67 over 3. And those values are, as you saw, about 8.06 and about 2.604. Which one of these can I throw out? Why can I throw out 8.06? Somebody say it? It's too big. Remember, our domain of interest for this problem was 0 to 7. Not that the polynomial isn't defined for bigger values, it's just that it's not of interest relative to this problem. So we're going to throw this one out. So the only other critical point that's left then is 2.604. Okay, not so bad. So that's a critical point. The question is this a maximum or a minimum? How could you tell? You could look at the graph, or I like that, second derivative. We'll actually do both. There's 2 tests, and you should know both of them, despite the fact that Yuri's shaking his head saying, no, man, no, please. You should know both of them to figure out whether or not a point is a maximum or a minimum. So let's go through both of those. So for the first derivative test, is going to look like this. We've got x, our function, and the derivative, 2.6 something, 04. We know that it's 0 here. Let me write up the first derivative here. V prime of x was, 12x squared minus 128x plus 252. We need to test points on either side of this. So I would suggest, giving yourself a couple simple points, like 1 and 3. I don't think I need a calculator to figure this out. Putting in a 1 here and here, I get 12 minus 128 plus 252. Do we need a calculator to figure out what sign it is? It's going to be positive. If I put in a 3, 3 squared is 9, times 12 is 108. This minus, wow, let's see, it's going to be what, 400 something plus 252. Well, it's going to be negative. What's that telling me about the function? It's increasing, then decreasing. So if it's increasing, gets to a critical point, and then starts decreasing, what kind of point was this? That's a maximum. So that's your first derivative test. That guarantees that you're maximizing it as opposed to minimizing it. For sake of completeness on this one, let's take a look at the second derivative test. Because sometimes one is going to be more convenient than the other. It's just going to depend on the particular problem. So let's take a look at the second derivative test. Second derivative. Test. Yes?
If you put the first derivative to the graph and then you graph it, would you be able to define the maximum?
Yeah, it'd be, well, yeah, it'd be where it crosses the x-axis. But it has to be where the function is, the first derivative is positive and then becomes negative. Yes, so you could find it based on the graph of the first derivative. Sure. The second derivative test, I think in this one will work out pretty good. What does the second derivative tell you about a function? It's concavity. Now, near a maximum, what kind of a shape do you expect to see? Concave down. What about the second derivative would tell you that a shape is concave down? What's the sign have to be for?
Negative.
Negative. Yeah, so if the second derivative is negative, then you're going to have a concave down shape. So the first derivative, v prime of x, was 12x squared minus 128x plus 252. Second derivative is going to be 24x minus 128. Now if I put in about 2.6 something, 2.604 minus 128, even if that was a 3, 72 minus 128 is still going to be negative. That's all I really need to know, is that it's negative. So it has a concave down shape at a critical point. So therefore, by the second derivative test, .604 is a maximum. You only have to apply one. You don't need to prove that it's a maximum two different ways. Do whatever is most convenient. Sometimes it's nice and easy just to apply the second derivative test. Other times you look at that and go, there's no way I want to calculate the second derivative here. It's just going to depend on the problem. Yes, ma'am? Plug the critical point in. If the second derivative at a critical point is less than 0, then that critical point is a maximum. If it's greater than 0, then you've got a concave up shape, and then your critical point is a minimum. Okay. How's that first one? It's a good look at the kind of problems we're going to solve in this section. I'm going to do kind of a couple gentle ones to start with, and then we'll make them a little bit more challenging. So, is there any other follow-up on that one? Because this less than 0 tells you that the shape of the function there is concave down. So if you've got a critical point, that means that its tangent line is 0, or has a slope of 0. If you have a concave down shape here, then that point has to be a maximum. If the second derivative is greater than 0, it means you have a concave up shape, and that spot where you've got a horizontal tangent line must be in a minimum. So that's what's going on at those 2 points. Okay, thanks for the question. Let's try problem number 4. So a couple kind of warm-up problems, 1, maybe 2. They're asking you for a couple positive numbers that multiply to 185 and add up to a minimum. Let's see if we can't figure out what that's all about. So let me get the problem up on the board for you to take a quick look at it. There we go. So we want 2 positive numbers. The product is 185 and the sum is a minimum. Okay, so they're not giving us a whole lot here, but they're giving us enough. There's no picture that we're going to draw for this. We're not dealing with a box or something like that. We simply have the product is 185. Product of 2 numbers, so that's x times y. They also tell us that the sum of these numbers, they want to be a minimum. Well, what should I write for the sum? Sum would be the x plus y. Now I want this sum to be a minimum. Okay. Well, there's a challenge we have with this right now. And that is, this depends on 2 variables, right? We have an x and a y. We need it to depend on 1 variable. So is there any way that I can make this depend on 1 variable? All right, so this is 185 over x is equal to y. And if I replace that here, then I get s of x equals x plus 185 over x. For purposes of differentiation, you might find it convenient to write that as 185x to the negative first power. Okay. So now what? Well, there was no picture. We've got our function. What's next? What's it say on your sheet? Picture, function, interval. Now the problem told us that we have to deal with positive numbers. So it has to be 0 to, infinity. 0 to infinity. Let's work on the analysis part here then. For the analysis, I've got s of x is x plus 185 x to the negative first power. Where should we start with the analysis? Dylan, suggestions? Yeah, let's find the derivative. When the only thing you have is a hammer, everything looks like a nail, right? So we'll differentiate. 1 minus 185x to what power? Negative 2. Now I want to find where that's undefined or 0. Where is it undefined? That's 0. Because remember what this really is, it's 1 minus 185 over x squared. So it's undefined at 0, but that's not in our interval of interest. So the other problem that we could work on is figure out, well, where does this actually equal 0? All right, let's do that. We'll start by moving this to the right-hand side. And I get 1 equals 185 over x squared. multiply both sides by x squared. I get x squared equals 185. X equals plus or minus the square root of 185. But I'm just going to keep the positive root because the problem told me to. The problem said just worry about the positive numbers. So there you go. All right, nice. Well, if x is square root of 185, what does y equal? How can I figure out what y is? Yeah, substitute x in the original equation. Now there's one step I skipped, but I'll go back and fill in the gap in just a second. So 185 divided by x is going to be 185 over the square root of 185, which is the square root of 185. So those are your two numbers, root 185 and root 185. The one step that I skipped is actually showing that what I had was either a minimum or maximum. In this case, we wanted to minimize something. You could do it one of two ways. You could play around with the first derivative and do the first derivative test. Personally, I think this is pretty easy if you do it with the second derivative. What would s double prime of x equal?
Sorry,
370 x to the negative third. Okay. I want to check the point square root of 185. Square root of 185. Do I need to break out my calculator to do that? What am I looking to figure out from this? If it's positive or negative? I mean, can this be negative? No, it has to be positive. So if it's positive, what kind of shape do we have for our function at that point? Yeah, other down. So concave up. So this implies that square root of 185 is a minimum. Remember, because you have a concave up shape there. So square root of 185 is a minimum. This point represents a minimum for our function. Yay. You can double check these things by graphing them. There's nothing wrong with pulling out your graphing calculator. I'm going to cheat and do a little faster with Desmos, but you can do it on your graphing calculator just the same. So let's see. Where's Desmos? I can't believe I don't have it up. Okay. Desmos. Well, I have my priorities straight then. So y equals, is it x plus 185 over x. All right, you have to zoom out considerably. There you go. If you trace this close to the bottom, you should get something that looks pretty close to the square root of 185. You can verify that with your calculator as a square root of 185.